while ago, I stumbled across this program that approximated the Mona Lisa using nothing but triangles. Turns out this was an example of a genetic algorithm, which is basically Darwin's theory of evolution applied to code. Survival of the fittest, but instead of animals, you're evolving a solution to a problem. And if you know me at all, you know I had to build it for myself. I liked the idea so much, in fact, I built it twice. Here's another example of a genetic algorithm project I did, so I kind of lied, I did it 3 times, but if you want all the nerdy technical details, go check that out. And then I started thinking, this must be the tech that powers them darn Waymos, right? Nah, not really. Genetic algorithms learn essentially blind. The only feedback they get is their final score. Meaning what happens during their episode is essentially thrown out. This leads to needing thousands and thousands of agents and generations just to inch forward in progress. And that's when I started doing some more digging. I was like, okay, what do people use for these real problems? The answer was reinforcement learning. The core idea being, what if an agent learned from every single step instead of just throwing it all away? Reinforcement learning is a computational approach to goal-directed learning and decision-making, where the agents strive to achieve a specific objective by maximizing total rewards. The whole process being interaction-based so the agents can learn from their trial and error. There are 3 key elements to a basic reinforcement learning framework. The first being policy, the second being rewards, and the third being a value function. So here's the general agent environment loop that our agent will be facing. And if you can't read my handwriting, you're out of luck. At the start, the agent is at the starting position and the reward is 0. Our agent then takes an action on the environment. The environment then responds with a new state and a reward for that specific action. This action environment loop keeps going until we reach the terminal state. So thinking in this framework, we want to prioritize the long-term goals, not just the short-term goals. We call this cumulative reward return, which is G. In my grid world, every step gives a -1 reward and reaching the goal gives 0 reward. It sounds confusing at first, but this is a good way to make sure that the agent reaches the goal as fast as possible. Because if a state's value is -5, that means it's 5 away from the goal. And if a neighboring state is at -10, it's gonna pick the -5 state because it has a higher value. And that -10 state is 10 steps away from the goal. Over the course of training, the agent assigns values to states, which builds its value function, basically stating how much future reward it can expect from that position. The policy is then determined by picking the action that leads to the most valuable state at every state. And at each place in the grid world, the agent can make 4 actions: up, left, down, right. If the agent's value function is optimal, it'll show you how to get to the goal from each state. I'm not going to spend too much time here because I know even computer science people don't like math. But basically we have the formula that optimizes the agent's value function here, where Q is the value of an action at state S. The wiggly A determines our learning rate, which is how big steps we take when we're learning. R is our immediate reward that we just got from our action A. The other squiggle before the max is gamma, and that's how much we discount our future rewards. Gamma kind of discounts our future predictions because the further we go out, the less reliable those predictions usually are. And this whole formulation is for Q learning, and the 2 other algorithms, Monte Carlo and Sarsa, tweak this update rule very slightly. Sarsa swaps out that max for whatever action the agent actually took. Monte Carlo is actually very different from the other 2 as it's not TD. TD meaning temporal difference learning, and it just waits till the end of the episode before it updates its values. The TD algorithms, however, Q learning and Sarsa, they update at every step. So they're kind of updating as they're going along. So then I built a website where the agent's training can be visualized. All the environment and agent settings are on the left side. And in here you can change things like the grid size, the frame rate delay, the number of episodes, the max steps. But there's a few things I want to touch on that might seem a little bit confusing at first. The expiration determines what % of the agent's actions are random. Too little randomness and the agent won't explore enough, and too much randomness, the agent will explore way too much and basically just be a random agent. The max steps determine how many steps are in each episode. The checkpoint every determines how many episodes train in the back end before an update is shown on the front end. On top, we have our algorithm selection and we have our simulation mode selection. Again, the learning rate only affects Q learning and Sarsa, not Monte Carlo. In the middle, we have our 3 graphs where you can see the agent learning in real time. After training is started, the best policy found so far will be on the middle graph with its accompanying values on the right hand side. Then after training is complete, an agent will be spawned in at each checkpoint on the left hand side. Finally, we have our graphs on the bottom. The left hand graph shows the return we got at each episode. Both lines in these graphs should trend upwards, but the rolling average will be much more smooth since it only takes into account the last 20% of episodes. In the middle graph, we have the policy change percent. This graph tracks how often the best action from last episode changes in this episode. Over time, this should go down as the agent becomes more confident in its policy. Finally, we have the episode length graph, which shows how many steps it takes to complete an episode. This also should go down over time, just like the policy change percent graph. If this is stuck at the max step limit, that means you should probably increase the step limit so that the agent has more time to complete an episode, or it's a skill issue and all your parameters are messed up. Using the website, I compared the 3 algorithms on an arbitrary 9x9 grid. The only algorithm to not converge on the optimal policy was Monte Carlo. It was stuck at the max limit for a while, so it probably just needed more steps, which makes sense since it does start at random samples at the start. Q-Learning and Sarsa converge, but what's interesting is that Sarsa's policy kept changing slightly. This can likely be explained by the fact that when it estimates the future value, it uses whatever action the agent actually took, including the exploratory random one. The website is live too, so if you want to go try that out, definitely check it out. All the technical details for this project are on my portfolio, so if you want to get even more confused, check that out. Thanks for listening to my TED Talk. I definitely appreciate it. I have some more projects lined up, so you're going to have to stay tuned for those.